Okay, no questions? Uh-huh.
Is that recorded?
No. No. It's also being recorded on, for YouTube too.
Yeah.
Oh yes, Professor, are you recording?
Yeah, I'm recording now. All right, so we're talking about energy changes. If it's an object, then like water, liquid water. Let's see, this was 50.0 grams or milliliters of water at 25 degrees C. This is going to have some internal energy, U, which is equal to what? Yeah, eventually it'll equal that, but it's not U. There's no change yet. This is what we call absolute internal energy. The absolute internal energy is equal to
4.18.
yeah, but the potential energy plus the kinetic energy. For objects like water, liquid water, about 50 grams of water, any energy changes with that will be associated with the temperature. They're either going to warm up or cool down. So, for example, here we can warm this water up 50.0 grams of water at what was the temperature that we did it at from last time?
Room temperature?
I think 100 degrees C. So we warmed this up to 100 degrees C.
I think you did 25 grams, not 50.
Oh, did I do 25 grams? Sorry. All right. I just want to. This is before the break. All right, so if we go 25 grams of water at 25 degrees C and warm it up to 25 grams of water at 100 degrees C, there's going to be an internal energy change. And so the final internal energy, it's going to be a higher energy. And this is going to be the potential energy final plus the kinetic energy final. And there are different ways we can write kinetic energy, E sub k or just Ke. I'll just write it Ke for this case. But was there any change in potential energy? No. We have liquid water, we still have liquid water. So there was no change in the bonds or the hydrogen bonding interactions or any of that kind of stuff here. The only change was in terms of kinetic energy. And so we know that the delta U is equal to delta PE plus delta KE. And since there was no change in the potential energy, the change strictly in terms of kinetic energy. And so whenever there's a change in energy of an object, it either heats up or cools. And so the object can heat up or cool. In this case, the object heated up. And that's going to be related to heat, Q, which is in this case MC delta T, MC delta T. That is if M is the mass and then C is the specific heat. And so we have different objects here, and we'll have different specific heat so we can determine the change in the kinetic energy. Over here, so lead, specific heat of lead is 0.13. In fact, that appears to be the smallest. Let's see, is there anything smaller than 0.13? So let me scroll down. We'll look at liquids. No. 0.13 appears to be the smallest. Actually, gold. Gold is also 0.13. I know to 2 sig figs, but not to 3. So I don't know which one's lower, gold or lead, but they're about the same. And what that means is that it takes very little heat to cool or to warm lead and gold. They heat up and cool down rapidly. Whereas things with a much higher specific heat, like ice would take a lot more heat to warm up or cool down. That's a higher specific heat. What has the highest specific heat? one's wrong now.
Liquid water.
Hydrogen gas.
Hydrogen gas is an odd one.
Protein.
But hydrogen gas is unusual. Liquid water is normally the one, but the hydrogen gas is very odd. And so hydrogen gas, they're talking about using hydrogen, you know, for a traditional nuclear reactor. Traditional nuclear reactors are cooled with, do you know what they're cooled with?
Helium?
With water.
Oh.
Water cooled. But they're looking at these new reactors that are going to be cooled with
I
hydrogen.
remember.
I thought they would have used deuterium.
Is hydrogen stable?
Hydrogen's not, but it's stable as long as there's no oxidizer around. So if you keep hydrogen separate from the oxidizer, then it's stable.
I don't know, it could be an accident waiting to happen.
Yeah, that's true. That's why, you know, when the hydrogen fuel cell cars came out, and there are two, I don't know if Mercedes is still offering one, but Mercedes used to have a hydrogen fuel cell car, that maybe they still do. And I talked to one guy who got one, and you can only lease them. And so he leased it, and I asked him, isn't it like what you say, an accident waiting to happen? And he said no, he's not worried about it. He's not worried about it because on the promo video, they took the hydrogen tank and flew up, I think, 30,000 or 60,000 feet above sea level and dropped the tank in the desert, and it
I'm
and
more
it
scared of
survived.
an oxidizer getting in there and causing
What's that?
combusting. I'm more scared of an oxidizer getting
No, the opposite would happen because it's under very high pressure. And so the thing when you work with compressed gases is they can fill up the room in an instant. So if you have a compressed cylinder of hydrogen here, what happens with compressed gases a lot of times is people die of asphyxiation because it just purges all the air out of the room. And there's no more air left. And so you have to go to gas safety courses when you start working with compressed gases. But yeah, the gas leaks out and then that's a big problem. But hydrogen's a bit unusual. You know, water has a very high specific heat, and so, and in fact, this high specific heat is really important for life. And so, like I said, the first chapter of biochemistry just deals with the physical properties of water. All right, so we calculated how much heat is this going to take? What was the number we calculated for the change in the internal energy, or how much heat we have to add to this to warm this water up?
7,845 joules.
All right, now, there's a sign convention. Did I already write that down? The sign convention? The sign convention, well, I have to talk about this because sometimes we have to remove heat. If we have to remove heat, then we either say we have to remove 7,845 joules or minus 7,845 joules is required. And so if Q is greater than 0, we call that endothermic. And we have to add heat. If Q is less than 0, that's exothermic, and we have to remove heat there. But there's no such thing as negative 7,845 joules. It's the same thing as like money. Let's say you owed somebody money. You owed somebody $20, so that's minus $20. But you can't pay them with a minus $20 bill, can you? Does such thing exist? No. And so it's the sign convention. Energy is always positive. And the direction of exchange, it depends on your reference point. I mean it's negative or it's positive. This is why we have this, to define the direction of exchange because of the first law of thermodynamics. The first law of thermodynamics states what?
Energy is conserved.
Right, energy is conserved, it can neither be created nor destroyed, so if somebody gains heat, like this water, somebody else has to lose the heat. And so we can say the system's one partner in the exchange, and the other partner is the surroundings. And so whatever the system does, whether it gains positive or loses negative, then the surroundings must be the opposite, and so we just change the sign. And so if the system's positive, the surroundings is negative. If the system's negative, the surroundings must be positive. And so this energy comes from somewhere. Now, what happens if I try to go above 100 degrees C? Do you know what happens? If I try to go above 100 degrees C, I'm not going to be successful for liquid water. It's going to start to boil. And when it boils, then what I end up with is I end up with steam. And the steam is going to be at 100 degrees C. And so, you know, the liquid water will stay at 100 degrees C until all the water's boiled. There's going to be no temperature change. That's called a process, like boiling, process of boiling. Or it's a reaction, you know, reaction or process. For reactions and processes, we look at those differently. So when we boil water, the temperature doesn't change. The temperature stays the same. We could have other processes. So what I want to do is I want to get this amount of energy from not water. I want to get this amount of energy from burning methane. So the states are very important in thermodynamics, and so you have to write down the states here. So for example, liquid water has a different specific heat than gaseous water. Steam's specific heat is 2.08, and ice has a specific heat of 2.11, and liquid water has a specific heat of 4.18.
Wow, it's double.
Yeah, it's about double, so we have to write that in. And so I want to do this. There's going to be some energy, plus energy, associated with this. And so this would be a reaction or process. So I should try to match this here. So what I want to do is I want to burn my methane. And so I'm going to have methane and oxygen gas. This is my mixture here. And then I'm going to go to CO2 gas plus 2 liquid waters. Because I'm going to burn this at 25 degrees C. So this is going to be at 25 degrees C here. And so for reaction or process, we treat these a little differently here. Heats of reaction. And so what we do is we do this. This is going to be an exothermic reaction. So when we burn it, the temperature is going to climb up, and then we just wait for everything to cool back down to room temperature. And so this way we can get the reactants at 25 and the product at 25. The same thing. If the reaction is endothermic means it's going to absorb, it's going to cool down, and then warm back up. So we wait. Okay, and the reason we do this is so that the kinetic energy doesn't change. If we didn't wait for it to cool back down, then we would have 2 terms in our change in internal energy that we'd have to deal with. It's not hard. I mean, it's not a big deal. We could figure it out. For example, if it went to 50 degrees C rather than 25 degrees C, then we just have 2 terms we have to deal with. We have to deal with the specific heats of the objects from the kinetic energy part and the potential energy. But it's just much easier if we don't deal with that. You know, and so again, we get the same thing, U initial and U final. And then we're going to have a delta U. In this case, delta U, which we want this to lose a certain amount of energy. In fact, I want this to lose 7,000. Okay. So I'm going to call one of these my system, the other the surrounding. So it doesn't matter which one you call which, you know. Just one and the other. In fact, I'm not even going to call. I want this to lose minus 7,845 joules. And I want this one to gain that much. And so the delta U is going to equal the delta in the potential energy plus the delta in kinetic energy. The delta in kinetic energy, fortunately, is 0, since starting and ending at the same temperature. But the delta in potential energy, that's what we're after. So how can I figure out the delta in potential energy? One way we could figure it out is we could take U final minus U initial, but this is never done. Why?
It's inaccurate.
Yeah, it's inaccurate, you know, and figuring out the potential energy is the problem. The kinetic energy is easy, because we have the kinetic molecular theory to tell us the kinetic energy, but this is the problem. Determining absolute potential energies is not done with any accuracy, enough accuracy. And so we never actually do this. Instead, we're going to have to figure out a different way of doing that. And so the different way that we're going to do that is, this is the amount of heat that we need to warm that up. And so we're going to call this Q here. But delta U is either extensive or intensive. We can do it either way. Delta U is typically an intensive quantity. The normal units for delta U are kilojoules per mole. So this is intensive, the actual delta U. Whereas the Q, this is going to be intensive. The amount of heat depends on how much methane you burn. The more methane you burn, the more heat you're going to get. Whereas delta U is typically an extensive, or what am I doing? I'm doing it backwards, sorry. This is extensive, it depends on the amount. And this is intensive, sorry. It does not, well, it's just a ratio. Well, obviously it depends on the amount here, but it's always normalized to kilojoules per mole. Kilojoules per mole of what? Because when I look at the reaction, I have 1 mole of methane, 2 moles of oxygen, 1 mole of CO2, and 2 moles of water. So it's per mole of what? Well, it's usually per mole of whatever you're burning, methane. And so this is per mole of methane here. And since there's this kind of mismatch here, you know, this is extensive, this is intensive, then when we do this, we get this other equation. And so this is Q for an object, we call it. This is going to be Q for a reaction or process. And the Q for a reaction or process is going to depend on the amount. How many moles are we going to burn? Are we going to burn 1 mole? Are we going to burn 10 moles, or what? Times delta U. Because delta U is going to be in kilojoules per mole. Well, how do we figure out what delta U is? Something we need to do. Well, that's what we'll talk about now. We want to figure out how much heat we can get from burning a mole of methane. Now, when we're going to burn a mole of methane, we have to figure out this. Do we want to burn the mole of methane at constant pressure or constant volume?
I would recommend constant pressure.
I'd recommend constant pressure too. But the problem is this. The problem is that when you burn it at constant pressure, we have to use a calorimeter. We have 2 types of calorimeters. Do you know what the 2 types of calorimeters are?
Bomb and teacup.
Bomb and coffee cup.
Coffee cup.
Is it going to be easy to burn it in a coffee cup?
No.
No, but even if you get fancy coffee cups that aren't made of styrofoam, is it easy to burn it?
No.
No.
Because it might destroy the coffee cup.
Still not
Well,
easy.
even if you get rid of that,
Possibility. You don't know if
then make it out of ceramic. You know, the coffee cup calorimeter, it doesn't have to be a literal coffee cup. We can make these out of insulated ceramic or glass or whatever, and try it that way. You know, you use these 2 styrofoam cups and then some kind of lid and stir that has a glass stir and thermometer. That's kind of what you guys used, right? So this is constant pressure because, you know, if gas builds up in here, it can leak out. Or if gas gets consumed in here, it can leak in. And so it can maintain constant pressure with the atmosphere. But we're not going to burn it in the coffee cup. Instead, probably the safest and the easiest way is to burn it in a what? Bomb, right? And so let's take a look at a bomb, the construction of a bomb. This is it. You know, there's some ignition wire here. This is mainly used for combustion reactions. It's a lot easier. And so you put your reactant in here. In this case, methane's a gas, so you fill this chamber with gas and oxygen, and then you ignite it. You ignite it, and then what's going to happen is all the heat has to go somewhere. And so after you ignite it here, you're going to be left with CO2 and water. The CO2 and water is going to get hot, but not only will the CO2 and water get hot, but also the bomb is going to get hot. This is the bomb in here.
Steel bomb.
And then the steel bomb is going to be in contact with this water reservoir. And this water reservoir is encased in another bomb here. And so the whole thing's considered the bomb. And so all the heat that's generated here leaks into the bomb and warms up the bomb. So when we warm up the bomb, we're actually warming up the bomb, the water, the thermometer, et cetera, everything. Not only that, but some heat leaks out from the bomb into the air and the countertop. And so what we first have to do is we have to first figure out, this is an object, we first have to figure out the specific heat of the bomb, right? And so to figure out the specific heat of the bomb, what we do is we do a calibration. And so how can you calibrate the bomb? Well, it's actually, if you know how much heat is given off by something, it's actually pretty straightforward to calibrate the bomb. You'd have to do an experiment. And so let's take a look at calibrating the bomb calorimeter first. All right, so for example, if we look at some of these, 35, a sample gives off 5,228 calories when burned in a bomb calorimeter. The temperature of the calorimeter assembly increases by 4.39 degrees C. Calculate the heat capacity of the calorimeter in kilojoules per degree C. So we know how much heat went into the bomb, and we know the temperature increase. And so the heat capacity is just going to be the calories per degree C or the joules per degree C or the kilojoules per degree C. In this case, they want kilojoules per degree C. And so here we could figure it out. But how do they know 5,228 joules went into the bomb? Well, that's what they're telling us. No, it's not just the water that's warming up. Yeah, there's a bunch of other stuff that's warming up. And so we'll take a look at how they figured that out. Well, the following substance undergo complete combustion in a bomb calorimeter. The calorimeter assembly has a heat capacity. Okay, so this bomb, each bomb calorimeter has a unique heat capacity. You know, it depends on how much metal they use, how much water is in the tank, and not only that, it changes because the amount of water might evaporate or change day by day. And so this bomb calorimeter is 5.136 kilojoules per degree C. That's the heat capacity. So how do they figure that out? Well, they figure that out by performing a calibration. And so let's look at number 37. A bomb calorimetry experiment is performed with xylose, which is C5H10O5 solid, as the combustible substance. The data obtained are, okay, so they have the mass of xylose burned. So they burned 1.183 grams. They have the heat capacity of the calorimeter. And so here, it's already been calibrated. This is how much. And so this is not calibration. What we got to do is we first got to do a calibration of this. And so we'll skip through, and then we'll come up with this one here. We could either do like 41, let's take a look at 42. 42, salicylic acid, C7H6O3, which is a solid, has been suggested as a calorimetric standard. So this has been suggested as a standard. You know, normally with standards, what do we want? Like a primary standard. What do you want in a primary standard?
Something that's stable.
Yes, it's gotta be stable. So salicylic acid is stable. This includes forming hydrates. We don't want things to form hydrates, you know, or if it does form a hydrate, we want a stable hydrate, so we don't have to dry it. You know, drying is a hassle. It just adds a lot of extra work. And so if you have a stable hydrate, that's okay, or no hydrate, that's even better. So salicylic acid, probably aren't gonna have to dry it. If it's a primary, if it's being suggested as standard, you don't wanna have to dry it. What else?
Pure.
It has to be pure, so that means this stuff is easy to synthesize and it's highly pure, and hopefully it's cheap too. And salicylic acid is cheap.
Hold on a second.
It's yeah, salicylic acid, this is the original aspirin, you know. The original aspirin is salicylic acid, and then it was a little bit too acidic, so they buffered it, so they have methyl salicylic acid. But anyway, it has been suggested as a calorimetric standard, so we're going to use this to calibrate the bomb. It's heat of combustion, so we know 1 mole of salicylic acid generates this much heat, and the negative means it releases this to its exothermic. Right. But again, there's no such thing as negative energy, it's all positive, so this is just the direction of exchange, it's losing it to whatever else. From the following data, determine the heat capacity of a bomb calorimetry assembly. That is the bomb, water, stir, thermometer, wires, and so forth. You know, everything else. And so the first thing we got to do is we got to calibrate the bomb. And so let's take a look at this particular problem here. Just set it up over here on the side of the board. So this is number 42. This is the bomb calibration. So what we're going to do is we're going to burn some salicylic acid. So salicylic acid is C5H10, or no, sorry, wrong one. C7H6O3. C7H6O3. It's a solid. The state's important here. Actually, this might have been one of the unknown acids, salicylic acid, plus O2. We're going to burn this. And this is going to produce CO2 and water. Do we have to balance this? Not necessarily. I mean, we don't need to balance this because we aren't really doing much. We just need to figure out how many kilojoules per mole. Actually, we don't even have to figure that out because they tell us how many kilojoules per mole we have. But we could balance this just for practice. So that's going to give us 7 CO2s, and then 6 hydrogens, means 3 waters here. And so I have 14 plus 3 is 17 oxygens. I have 3 plus what gives me 17? Yeah, it's got to be 14. So that's it. This would be balanced, but it wasn't necessary to balance this. Now, it says here the initial calorimeter temperature is 23.68 and the final calorimeter temperature is 29.82. But what are we going to do with this? What we're going to do with this is this. We're going to say, okay, this is going to be at 23.68 initially. what should be the final temperature here?
23.68.
It's gonna be
Right.
23.68. It's weird, but that's it.
Constant temperature, potential energy.
Right. And the delta U here is just going to be the change in potential energy, right? Which is going to equal,
Oh, 3.023 times 10 to the third kilojoules, and negative if you want to count it as exothermic.
right,
We're just counting for energy.
okay, this is our change. The delta U is going to depend on how much. Now, this gets all mixed up sometimes because delta U normally is intensive, but this is going to be extensive because are we going to burn a full mole?
Yes. Complete combustion, right?
Yeah, it's complete combustion, but are we burning a full mole of it? No. We're only burning 1.201 grams. That's not a full mole. And so this is how we're going to settle this. This is going to be our Q, the amount of heat that's released from this. Now the amount of heat is going to equal, Q is equal to the amount times delta U. And so do you see this little thing I did here? You know, normally when we do delta U, it's per mole of salicylic acid. It doesn't matter how many moles of the other stuff, it's per mole of salicylic acid. And so my delta U here is going to be, is given as, its heat of combustion is minus 3.023 times 10 to the third kilojoules per mole. Does that make sense? But am I going to get 3,023 kilojoules from this?
No.
No, not even close. Because I don't have anywhere near a mole of this. And so actually, how much of this am I going to get? Well, how many moles did I burn? Well, let's figure out how many moles I burned. And so the amount is 1.201 grams of salicylic acid. I'll just call it SA for short. Now I need to figure out the molar mass of salicylic acid. So I have 7 carbons times 1201, which is going to be 84.07, is that right? Yeah. 84.07. Then I have 6 hydrogens. 6 hydrogens is easy. 6 times 101. And then I have 3 oxygens. That's easy too. 3 times 16 is 48. So it's 13.
138.
138. And so 1 mole of salicylic acid weighs 138.13 grams. And so I'm burning just a fraction of a mole. Honestly, how many moles is that?
Is it
1.201 divided by 138.13. It's only like 0.008 moles, so I'm not going to get that much heat. If I burn a full mole, I get this much. And so the amount of heat is going to be this. It's going to be minus 3.023 times 10 to the third kilojoules per mole of salicylic acid. And so let's see how many kilojoules I get from this. So this is going to be times 3.023 times 10 to the third. Actually, 26.2 8 Looks like I'm allowed 4 sig figs. 4 kilojoules. Okay, where's all that heat going to go to? All that heat's going to go into warming up the bomb. So my delta U, the change here is going to be, this is negative. Delta U is going to be negative 26.28 of 4 kilojoules. So I could either express my delta U in terms of the extensive, the amount, or intensive. This. Depending on the problem, switch it. Okay, now the bomb, what happened to the bomb? The bomb consists of all that apparatus, and not only that, the rest of the universe. And so the bomb started at 23.68 degrees. So we have one bomb at 23.68 degrees. See? And then it's going to absorb plus 26.28 kilojoules. That's my delta U. And then I'm going to have a bomb at 29.82. And so this is going to release the maximum amount of heat. This is going to release the maximum amount of heat because we're going to wait until all of it cools back down, and then all that heat gets pushed into the bomb. Now the weird thing is, once the reaction is done, there's no more reaction left. This disappears. We still have the product left, and the product's going to warm up too. And so that's going to be incorporated into a bomb here, but basically this is it. And so our delta U here is equal to plus 26.28 kilojoules, and this is going to be our delta PE plus our delta KE. Did the potential energy of the bomb change?
No.
No. So the potential energy is 0, and so this is just equal to the change in kinetic energy, which is just going to be the heat, you know? Kinetic energy is heat. It's either going to warm up or it's going to cool down, which is going to equal the, do I want to weigh the bomb? Like MC, we're not going to weigh the bomb. In fact, we're just going to call it the amount times C times delta T. Well, how many bombs do I have? I only have one bomb. If I had multiple bombs, then put that in there, but there's only one bomb. Since there's only one bomb, I'm just going to call it C times delta T. This is what the book does. And so I solve for C. C is equal to Q over delta T. Well, Q is the amount of heat. And so Q is plus 26.28 kilojoules. And my delta T, well, the delta T is T final minus T initial. T final is 29.82. T initial is 23.68. And this would be in degrees C. So this is going to give us the heat capacity of the bomb in kilojoules per degree C. And so we'll take that. What did you guys get? The denominator is only going to give us 3 sig figs. So we're only going to get the heat capacity of 3 sig figs, unfortunately.
I got 4.28. Oh, 1/3.
So 4.28 kilojoules per degree C. Ideally, we should have burned more salicylic acid, so we could have gotten it to four sig figs. It's a lot of work just to get 3 sig figs.
Oh, but
So what we do with this is once we get the bomb calibrated, and so we know how much heat's generated, then we'll insert some number of grams of methane. Insert some number of grams of methane, burn it, and see how hot the bomb gets. From how hot the bomb gets, we can figure out how many kilojoules were evolved for that many grams of methane. And so we can get kilojoules per gram of methane, but typically it's written in kilojoules per mole, so we'll just convert grams to moles and we can get kilojoules per mole of methane. And that's what we end up with. So once we do that, then we can figure out how much methane we need to burn. And so what I want is this. I want to know what is the heat of combustion of methane. Well, fortunately, somebody else has already done the work, and so I'm just going to look it up. Do we have the heat of combustion of methane?
You guys search it up.
Yeah, so we're going to just search it up. But when you search it up, you have to be aware of one thing.
false information.
No.
Finding the right website? Finding the right website?
Yeah, the right website. We want to definitely use the right website. Like Topper, I don't know if this is reliable. What do you think?
No,
No?
I don't trust myself.
Check the second one and it's the same.
Oh, how about NIST? NIST is probably pretty. This is National Institute of Standards and Technology. They have a budget of billions of dollars. I think they probably have it right.
My budget is 20.
And it says .gov, so it means
Yeah, the government has
20 cents.
a lot of resources. Okay, so we have it. Actually, this is good. They're telling us different people. So, for example, Chase in 1998 got negative 74.87 kilojoules per mole. What is this? Gas phase? This is combustion? That's too small for combustion.
Yeah, this is gas phase though in chemistry data.
Yeah.
There's constant pressure, heat capacity.
Yeah.
Constant pressure,
Constant pressure, heat capacity,
gas phase,
gas phase.
reference.
Yeah. All right. So this one is another one, 889 kilojoules per mole. But what is HHV? You know, we look methane, ethane, propane, butane.
Let's say what's next, pentane.
Yeah. 880 kilojoules per mole. 889 kilojoules per mole. Copper. 800 kilojoules per mole. 880 kilojoules per mole. So it would be good to have a reliable source. This is in calories, 50,000 calories. Here.
Man, that's a lot of calories. You live like 25 days off that.
Wikipedia surprisingly has decent data. You know, I know a lot of instructors don't
trust Wikipedia.
trust I don't trust Wikipedia for most things except for these numbers are pretty good. But other stuff, it depends on who authored it. Okay, so if we go to Wikipedia, what do they have for heat of combustion of methane? But regardless of this, this is what makes thermodynamics tricky. What makes thermodynamics tricky is we can get a number, minus 880, minus 889. It'll make a little difference. But there's something else here that's hidden that you don't see. And that is, did they burn this under constant volume? Bomb is constant volume. Or did they burn this under constant pressure? Because normally, okay, we'll burn it in a bomb. And when we burn it in a bomb, you know, the volume can't change. However, if we burn it at constant pressure, then the volume can change. And so we do have the heat of combustion. We have the heat of combustion in our book here. Actually, what happened to my book? So I could look up the heat of combustion. In fact, the heat of combustion we could also find in Appendix D of our book. It's probably pretty reliable. This book is updated fairly frequently. And so we go to Appendix D. These are electron configurations we'll be talking about in the next chapter, chapter 8. And in Appendix D, we have this. Do you see CP? You know what that stands for?
Constant pressure.
No.
No?
Yeah, half of it. This P stands for constant pressure, but the C does not stand for constant. What does the C stand for?
Specific heat.
Well, specific heat specifically for gram, you know, per gram. And so the specific heat has the units of, yeah, it's the heat capacity. Heat capacity, we don't have to specify the grams. We wouldn't call it specific heat because if you look at the units here, it's joules per mole per Kelvin. The Kelvin is the same as degree C. And so specific heat has to be joules per gram per Kelvin or joules per gram per degree C. But heat capacity can be in any units, like per bomb, joules per 1 bomb per Kelvin. That works. And so here we have this specific, why would they put the specific heats there? That's wrong, right? This is not specific heat. This is heat capacity at constant pressure. And so we have to worry about, are we doing things at constant pressure or are we doing things at constant volume? It makes a difference. Why would it make a difference? It makes a difference because of work. When you're in a bomb, the volume can't change. If the volume expands, then work has to be done to expand. It's like blowing up a balloon. Work has to be done to blow up the balloon. Also in Appendix D are acids. This K value tells us the strength of the acids quantitatively rather than qualitatively. So different acids here. Here we have bases. Bunch of bases. Here we have the solubilities, essentially. You know, when something's insoluble, you know, how insoluble is it? Well, these numbers tell us that. These aren't strictly solubilities. These are more complicated. Here we have these things which are called complexes. We talked a little bit about these. They're formed from Lewis acid-base reactions. Here we have the redox chart. Familiar fluorine up here, but here we have oxygen difluoride, ozone, this kind of disulfate type thing. This is very unusual charge for silver, silver 2+. This is very unstable, 1.98. That's why we don't see silver 2 in any compounds. Cerium 4. So this is a more comprehensive list of redox. It's half a page. It's another page. When we have charts like this is a lot, but what's really helpful is to go through and read through this. And then you have a lot more familiarity with oxidizers and reducers. You know, you don't memorize it, but you just read through it once in a while. It's helpful. The base chart is a lot bigger. You know, on our base chart, water was at the bottom. This one, magnesium hydroxide, is at the bottom. And then we have the isotopes, which we talked about. It was appendix D, so unfortunately got rid of it. It's also in our chapter, heated combustion. Let me just search it. So we'll just use some data here and then take a look at the calculation. So,
Let's search bar for mapping.
yeah. All right.
That's an interesting one. Thermal cleaning. We'll consult that.
Well, we'll just use the other table, which is the minus 880. The heat of combustion of hydrocarbons.
Methane at 802.
Thermal fluids, we'll just do this one, but the situation is
Methane as a liquid.
this. If we burn this salicylic acid in a bomb, and we burn methane in a bomb, no work can be done. And so when we look at the other way of stating out the first law of thermodynamics, delta U is equal to Q plus W. Any change in energy is going to result in either heat and or work being done. And so this is going to be exchanged with the system and the surroundings. So we have a sign convention for heat and work. And so when we look at Q, Q is, did we do greater than 0, then this is endo. If Q is less than 0, this is exo. And so if something gains or loses, it has to go to someplace else. So if the system is endo, then that means everything else must be exo. And so we just change the sign. And everything else is just called the surroundings. If the system, whatever we're interested in, either object or reaction or process, is exothermic, then
The rest of this
yeah,
is
it's got to be opposite in sign. Now, the same thing with work. If work is greater than 0, then what we say is that the work was done. If the work is less than 0, then we say that work was done. But who did the work? So that's why I'm going to label this here. So if W of the system is greater than 0, then W of the surroundings must be less than 0. And so it's kind of weird to think about, but if the system does work, then what happened to the surroundings?
work.
You got work done.
Well, if the system does the work, then the surroundings didn't do any work.
They
But-
received work.
it received work. So
Received your service.
that's probably pretty good. So if the system does the work, then the surroundings benefited from the work, right? It received the work, and so the surroundings had work done. So this is kind of weird to think about. Let's say the system lost 100 joules doing work. Well, where did that 100 joules go? Into the surroundings. All right, now, in other words, we're going to come up with this. This is the same thing. Work of the system is equal to minus work of the surroundings. So energy is conserved. So whatever energy is exchanged, so energy can be exchanged in the form of heat. This is energy exchanged in the form of heat. As heat. And we use signs to keep track, whether it's negative or positive. And W is going to be energy exchanged as work. Okay, there's that, and then there's one other thing that's kind of weird about this, and that is delta U is what we call a state function. A state function is, all that means it's always the same. So if we burn a mole of methane, we're always going to have the same internal energy change. If we burn a mole of salicylic acid, we're always going to get 3,000 kilojoules released. But the weird thing is that Q and W are not state functions. Q and W are what we call path-dependent functions. So these are path-dependent. And so the amount of heat and the amount of work depend on how it's burned. So I'll just say amounts change depending on path. So, like a state function would be like the distance, like the line of sight or the direct distance from, let's say, your home to school. The path-dependent function would be, depends on which path you take. If you always take the same path, then it would be the same, But sometimes you take different paths, depending on traffic or whatever else is going on. And so the amount of time or the amount of distance could change depending on that. And so, so something like this here, if we burn this, it depends on how we burn it. Do we burn this in a bomb? If we burn this in a bomb, it's constant volume. So in a bomb, if we burn this in a bomb, it'd be constant volume. And the reason that's important is because of this, because of work. The amount of work depends on this. For example, if the volume doesn't change, then there's no work in blowing up the balloon, basically. However, if we do this under constant pressure conditions, then the volume might change. And so let's take a look at this first reaction. The reason why they want to make this a standard is because of this. Here we have 7 moles of oxygen gas. 7 moles of oxygen gas at around, let's say 24, 25 degrees C is going to be how many liters?
This is at constant volume. Right?
24.5.
Yeah, around 24, 25 liters per mole. So times 7, it'd be like 175 liters. If I had a mole of this salicylic acid, a mole of salicylic acid is 138 grams. Most solids are around 2 grams per milliliter. And so this would be around 70 milliliters. 70 milliliters is about 0.07 liters. So this would be like 175 plus 0.07. And so it'd still be about 175 because the volume of this is so small compared to the volume of this. Right? And so this is going to be about 175 liters. Okay, I have 7 moles of CO2. About how many liters is that?
You're saying
175 liters. And then 3 moles of liquid water. 3 moles of liquid water is, well, it's 18 grams per mole. So that'd be 36 plus another 18 would be what, 40, 50 milliliters at the most? 54 milliliters.
Yeah.
Okay, so if I have 54 milliliters, it's 0.05. And so this would be 175 plus 0.05, so it'd be 175.05. And so solids, you know, this is about a gram per milliliter, this is about 2 grams per milliliter, so there's not much of a change in volume. In fact, it's negligible, it's such a small change in volume. That the main thing is the gas. So we start off at about 175 liters, we end up at 175 liters. So if we did this in a bomb, there wouldn't be big pressure built up, you know, because we're not forming gas, and there wouldn't be a reduced pressure because we're not consuming gas. So it's not going to explode, it's not going to implode. In fact, I can make this bomb very flimsy because it doesn't have to withstand high pressure. Does that make sense?
Yes.
Yeah. And so this we don't need to buy an expensive bomb. How about this one? Do we need to buy an expensive bomb for this one? Okay, so let's take a look. I have 1 mole of methane, 2 moles of oxygen. So that's 3 moles of gas. 3 moles of gas at about 25 degrees, well, it's going to be around how many liters?
3.
This is going to be 75 liters. And this is going to go to 1 mole of gas. 1 mole of gas is 25 liters, and then 2 moles of liquid water. 2 moles of liquid water is 36 grams, which is 36 milliliters, which is 0.03 or 0.04. We'll go 0.04. So we're going from 75 liters to 25.04 liters. This bomb has to be sturdy, otherwise it'll implode. Right? Can you see it's going to implode?
Yeah.
Because you're going to go from 75 and it's just going to suck the volume in. And so this has got to be a really beefy bomb, otherwise we're going to have an implosion. And so if we do this in a sturdy bomb, then there's going to be no volume change. If there's no volume change, no work was done. So we don't have to worry about it. We don't have to worry about work. And all that change in internal energy is in terms of heat because there's no work. And was there any work down here?
No.
No. And so all that change in internal energy is just heat. But what if we didn't burn this? Oh, let me add that over here because the work is 0 because it's done in a bomb. Now, this is our delta U. Keep close to that. And over here, the work was 0 because it was done in a bomb. That's if we do it in a bomb. Oops, I don't know if I wanted to erase that. I'll leave this up here. Now, if we didn't do this in a bomb, would we get the same amount of heat?
No.
And the answer is no. We would get a different amount of heat. However, if we didn't do this one in a bomb, would we get the same amount of heat? And the answer is yeah, pretty much the same because the volume didn't change, so no work was really done. Does that make sense?
Yeah.
Because this is why they want to use that as standard there. But here, if we do this, now the weird thing is, if we did this in a bomb, we're going to get a certain amount of heat, but if we did this at constant pressure outside the bomb, would we get more heat or less heat?
More heat, because it's sucking in. So if it was a teacup, it would suck in from the surroundings.
Yeah, that's the weird thing. The weird thing is we're actually going to get more energy by burning this. This is constant volume versus constant pressure. If we burn this at constant pressure, we have CH4 plus 2O2 gas. This is going to go to CO2 gas plus 2 H2O liquid. Now, if this went to 2 H2O gas, you know what? It'd be the same. Because if this were 2 H2O gas, then we're going from about 75 liters to 75 liters. So it wouldn't make any difference. But in this case here, I have my delta U. My delta U is equal to Q plus W. And so over here, we're going from 75 liters to 25 liters, 25.04, but the 0.04 we'll just ignore, because it's not going to make that huge of a difference. And so we're losing 50 liters. And so delta V here, which is the change in volume, delta V is 50 liters. Now we're going to say that this is the system here. So if the system loses 50 liters, this is delta V of the system, then what happened to the delta V of the surroundings?
It would gain.
It had to gain 50 liters. And so the system is minus 50 liters, therefore the surroundings has got to be plus 50 liters. Well, if the surroundings is plus 50 liters, that means the surroundings just had to blow up a 50-liter balloon. That's going to require work. And so how much work did the surroundings have to do to blow up a 50-liter balloon? Well, we can calculate that. The work of the surroundings is equal to P delta V. This is what we call PV work. PV work is the work that happens under constant pressure when there's gas that's consumed or there's gas that's formed. In other words, when there's a volume change, we have to worry about that. And so what we're going to do is we're just going to use normal atmospheric pressure. So we'll just say this is at 1 atmosphere before and 1 atmosphere after constant pressure. So we'll just say it's going to be 1 atmosphere, and delta V is going to be, the surrounding is going to be 50 liters. And so this just gives us 50 liters atmospheres worth of work. Well, if we have 50 liters of atmospheres worth of work, how many joules were done? Yeah, times 101.3 joules per liter atmosphere, which means that we just had 5,000. 5,006. What does it come out to?
5,051.
5,051 joules.
5,065.
5,065
Yes. Sorry.
joules, which is equal to 5.065 kilojoules. So the work did that. I mean, not the work. The surroundings did that. And so what does that mean for the system? If the surroundings had to do 5 kilojoules worth of work, that means the system must
It benefited.
benefited. And so the system must be gaining that, right? And so the work must be losing that. And so this has got to be minus P delta V to keep the sign convention right. And so the surroundings lost 5 kilojoules, therefore the system just gained those 5.065 kilojoules. So in other words, this. If we do this in a bomb, then we get a certain amount of energy.
Yeah.
But if we do this at constant pressure, we get a little bit more energy.
Because of the added work.
Yeah, because of the surroundings that have to do the work. And so this mixes everything up because the amount of heat depends on how you do it. It depends on the path. And it complicates things. Because we gotta think, are we doing this under constant pressure or constant volume? Therefore, we're going to come up with some ways to simplify this using symbols. And this is why when I'm looking for the heat of combustion, this is unclear. Is this the heat of combustion under constant pressure, or is this the heat of combustion under constant volume? I gotta be careful, because, and that means I gotta really check the website to make sure, are they doing this under constant volume, that is the amount they got from the bomb, or is this being corrected for the amount that they're getting from constant pressure? So I'm not gonna just use this without knowing that first. And so the way we're going to take care of this is this. If we're dealing with things under constant volume, then what we want to do is this is combustion. If we're doing combustion under constant volume, then we want to use delta U combustion. If we're doing this under constant pressure, then we have a new symbol. The new symbol is going to be delta H of combustion. So the basic difference between a delta U and a delta H is delta H adds in the extra factor of work that has to be done if you want to maintain constant pressure. Delta U and delta H are both state functions. And the way that delta H becomes a state function is we always do the same amount of work. This is PV work. Delta U is we just do no work. You know, work is equal to 0 here. Or at constant volume. And we ignore all other types of work. We're not going to do mechanical work or electrical work or any of that. We always do the same amount of work over here because this is the natural work of the chemical reaction. Natural work of a chemical reaction. Okay, so this U is internal energy, and what is H called? H is called enthalpy. And so what's the difference between internal energy and enthalpy? Well, it's kind of all the same stuff, but let's take a look at it in more detail here. And so let's look at the relationship between U and H. Delta U and delta H. All right, delta U is equal to Q plus W. These are path functions or path-dependent functions. And so they depend on the path. And therefore, the amounts are going to be different. The more work you do, the less heat. The more heat you do, the less work. And so it just depends on, this would be like a AA battery. If you have a AA battery, it depends on what you put it in. If you put it into a mechanical toy, you're going to get a lot more work than heat. If you put the AA into a flashlight, maybe you'll get some work and a lot of heat. You know, it depends. But the AA battery has a fixed amount of energy. It's always the same. That's a state function. What you do with the AA battery depends on the path, Q and W. And so different So this is state. And so Q is equal to delta U minus W, the amount of work. So the amount of heat we get depends on how much work we do. If we do a lot of work, then we aren't going to get as much heat. If we don't do any work, we're going to get a lot of heat. In a bomb calorimeter, we don't do any work, so we get a lot of heat. All that Q is converted into heat. Now, there's a tricky thing here, because we play loosely with intensive and extensive. Normally, delta U is intensive, Q is extensive, but here, just kind of making it the same in this case. But sometimes we'll modify this for the amounts. Okay. Now, we can always make the same amount of heat if we always do the same amount of work. And so we'll just always do the same amount of work. And this will result in the same amount of heat. And so we're going to do two things here. We're going to restrict the work, PV work only. So if we only do PV work, pressure volume work, that is the work of blowing up a balloon, then Q is equal to delta U minus a minus P delta V. And it depends on how big the balloon is and what the pressure is. But we got to make sure that the pressure doesn't change. If the pressure changes, then it screws everything up. So restrict to PV work only and constant pressure. Because if you're trying to blow up a balloon and the pressure is changing outside, it's going to impact how much work you're going to do. So it's better just to have a steady pressure and blow up a different size balloon. So what we have is delta U this is a state function. And pressure, and actually delta B here. Delta B turns out to be a state function too. Because delta V only depends on how big the balloon you blow up is. And so if you blow up a 50-liter balloon, then delta V is plus 50 liters. It's always the same. If you lose 50 liters, that is the surroundings blows up the balloon, then it's minus 50. And so this is a state function. P's also considered a state function. And so the difference between a state function and a path function is state function is always the same for a given amount. And so what that does is it changes Q into a state function. And so this is a state function, and this is a new state function, call it. And when we have this, we're going to call it Q sub P. That just means Q means constant pressure. And Q sub P is going to be defined as delta H. Delta H. And so when we're dealing with constant pressure, rather than using internal energy, we like to use enthalpy. And so if I combust methane at constant pressure, then I write it like this. We'll have methane plus 2O2 gas. This is gas. This is at 25 degrees C. And then rather than having the initial internal energy, I'm going to have the initial enthalpy like this. The initial enthalpy is equal to, well, I know what delta U is. Delta U is U final minus U initial. And so this is going to be U initial, here, plus PV initial. That's my initial. And then if I go to the final here, it's going to be CO2 gas plus 2H2O liquids. And the final enthalpy is going to be U final plus PV final. And then the delta here, this is going to be delta H. Delta H is going to equal delta U, which is U final minus U initial, plus P delta V. Delta V is V final minus V initial, and P is the same. It's just the pressure, external pressure. And so basically what enthalpy is enthalpy is the total energy factoring in how that total energy, this is the total energy of the system, right? But it's the total energy, so the enthalpy is just the same thing as the total energy, except we're keeping track if the surroundings donates some energy to the system, or if the surroundings takes energy from the system. So that depends on the volume. The volume's interacting, because when we look at this, does this factor in the surroundings? Do you know how big the surroundings are? What size room you're burning this methane in? Do you know anything about the surroundings here? No, this is strictly system. And so in order to keep track of this, because energy can be lost to the surroundings doing work, or energy can be gained from the surroundings by the surroundings doing the work. But the surroundings is not factored in here, but we're factoring in here. This is how the system interacts with the surroundings in terms of pressure volume work. And so we get that extra bonus in energy, or we lose some energy having to blow up the system and the surrounding. And so essentially it's the same. It's like the total energy, except now we're factoring in the surroundings here. And so delta H is it. And since we burn, what do you think we do most? We do things under constant volume or do things under constant pressure? We do things under constant pressure the most. So most of these combustion numbers here are delta H's, not delta U's. But are we sure? I'm just assuming that they're doing that, but I'm not 100% sure. So I wouldn't necessarily trust these combustion numbers until I knew, is that delta U or is that a delta H? Because I'm going to get more or less heat depending on if I do it under constant pressure or if I do it under constant volume. And so I need to be aware of that here. And so that minus 880 or minus 889, I don't know. And so, actually, are we out of time?
We have 1 minute.
We have 1 minute. And so I'll give you some numbers next time. We'll look at it, and we'll look at it more carefully.